Section 2.7 is about derivatives and rates of change. So if you recall from section 2.1, we were trying to find the slope of the tangent line. So here I've drawn a graph. Here's my function f. And here you'll see when x is equal to a, this corresponds to a point on the graph of f. And there's a tangent line, which is right here, and you see that that goes through the point a comma f of a. Now, the strategy that we used in section 2.1 was that we chose a second point near a. We could choose a point to the left or to the right of a. I'm going to choose a point on the right because it's a little easier for me to draw. And let's call this point x. Now the second point corresponds to a second point on the graph of f. So this point has coordinates x, comma, and then I'll go over here, f of x. And the strategy we used in 2.1 was to find the slope of the line that goes through these 2 points. And this line is what we call the secant line. And the idea is that as long as I choose x to be close enough to a, the slope of the secant line, which I can compute, should be close to the tangent line slope. So what is the slope of the secant line here? Well, I'm just going to use the slope formula from algebra. And we know that the slope is given by the rise over the run. So the difference in the y coordinates, so I have, that gives me the rise of the secant line between these 2 points. And I divide that by the run. Okay, so this here is what we would say is the slope of the secant line through the 2 points a, f of a, and x, f of x. Now, what I really want is the slope of the tangent line. In order to get the slope of the tangent line, I'm going to keep choosing values of x that get closer and closer to a. Okay, and I can do this from the left or the right. So here I'm approaching a from the right. Over here I'm approaching a from the left. Okay, and we remember this as the limit as x approaches a. Okay. Now, if this limit exists, we're going to define this to be the slope of the tangent line to f at x equal a. Okay. We have a special notation for this. It's f prime of a, and this is what we call the derivative of f at a. Okay, so this is our new notation, and the word that we're going to use to describe this is the derivative. It's just the slope of the tangent line to f at a, and it's just given by the limit of the slopes of the secant lines as x approaches a. So next I'm going to do an example. So what I want to do here is find the equation of the tangent line to f of x. This is a parabola. at x equal 5. The first thing that we're going to have to do to find the equation of any line is we need to find the slope, okay? And then we need a point the line passes through. So I'm going to first find the slope of the tangent line to the parabola at x equal a. Well, I'm going to use the definition that we just had, and the slope of the tangent line, m, is going to be given by the limit. So this was the definition we just had. And in this case, a is equal to 5. And f, of course, is this function. So I have the limit as x approaches 5 of f of x minus f of 5 over x minus 5. So f of 5 in this case is negative 5. So let's fill this in. We have limit as x approaches 5. Here's f of x. Here's f of 5. And at this point, I'm going to simplify a little bit. Now, if I try to take the limit, this is a rational function. I'm going to try direct substitution, but I can see that in the denominator I'm going to have 0. In the numerator I'm going to have 20 minus 25 plus 5. That's also 0. That's indeterminate, which means I have no info about the limit. I need to use some algebra to pull the limit out. So I'm going to try to factor So this factors as x minus 5 times x plus 1. And that's going to remove the, pesky factor that was causing this behavior. Remember, these functions are not going to be equal, but the limits will be equal. Now this is just a line, a polynomial, so I can use the direct substitution property to find the limit, and I find that this is equal to negative 6. So the slope of my tangent line is negative 6. And here I'm just using that definition. Now, the second thing I'm going to do if I want to find the equation of the tangent line is I'm just going to use the point-slope form of a line, which is this thing, to find an equation for the tangent line. So right over here, a point that I have on this line is, since f of 5 is equal to negative 5, I know that my line passes through the point 5, negative 5. And I know the slope from the previous question is negative 6. So the point slope form of my line is y minus negative 5 is equal to negative 6 times x minus 5. And this is the equation of my tangent line. The next thing you might want to do is graph your tangent line with your function to see if, to check your work. So that's something you can do here.